All right. Directions are find the area between these two curves, f of x equals x squared, g of x equals x cubed. Forgive my poor sketch here. That's your parabola. Okay, it's made it a little darker. Forgot my colored chalk. And your cubic function right there, right? So fairly simple, very, very simple functions for these two functions. But this would just be to show the process of finding area between two curves, and then you'll tackle some more difficult examples a little bit later. Okay, so without that, let's say that wasn't there, okay, I might want to sketch that myself or just graph it on my calculator to get an idea of what area they're talking about here. It appears to be, there's a couple intersection points, right? And this is some kind of area between two curves right here, right? But it's not bounded, right? This will go down forever, this will go up forever, and there'll be no bounded area there. Same thing over here, this little portion here is gonna keep going up forever, and it's not bounded. The only part that's bounded is this little section right here. Right? And that's the area I need to find. Just the concept of how big it is, it's pretty small, right? Because this would be the point 1, 0, as I have it marked, 1, 0, and this would be the point 0, 1 on your y-axis, okay? So it should be pretty small, and that's what we're going to find out. And the concept is that we take the area under the upper function of this region, that is the function that has greater values, which of course in this case is the quadratic function, right? That function's on top, right here is your quadratic, and the cubic function's below it, right? So the concept is if you integrate from 0 to 1, where they intersect, and that's important too, right? They intersect at that point, they intersect at that point. We know what those x values are, okay? So if I integrate from 0 to 1 for this quadratic function, that'll give me the area from here all the way down, right? But then I'm going to subtract from that the integral under, or the area under the cubic function, right, which would be this cubic function here and everything under that. So the idea is you subtract one from the other and it gives you this bounded region, okay? Or in other words, f of x minus g of x in this case. Okay, and that value there, remember that's a definite integral, that value should give me that area, okay? Provided I set it upright. It's very important that you put the greater function first, right? The upper function. What's upper, what has larger values on this interval, 0 to 1? The quadratic, right? If you square a number between 0 and 1, it's higher than if you cube a number between 0 and 1, right? After that, the cubic guy wins, of course, all right? What else? How did I get these? 0 to 1. In this case, very easy, right? I just looked at my picture. I knew that that region was from 0 to 1. That's where these two graphs intersected, right? Sometimes you have to do that algebraically. Let me come over here and show you what that would involve. When I say algebraically or some other method, right? We equate both the functions and see when they have the same value, okay? Or see which x values that x squared is the same as x cubed, right? And we can do that pretty easily. You can do that in your head. You can see here where it happens on the graph, and sometimes if the functions you're working with are more complicated, you won't be able to approach it this way. Okay, you might be forced to go to a graphical solution. But wherever these guys intersect are numbers you're really interested in, all right? Because that's where we're going to set our bounds for our integration. So the algebra here would be, well, we could do it like this. We don't really have to. We could set it to 0 since it's a polynomial function and factor it, right? And that gives you the two solutions, right? 0 and 1. You can see where we get those algebraically. All right, so let's do the calculus then. Very simple functions. We start with an easy one. Anti-differentiate. We're going to add 1 to that and divide by 3. We're going to add 1 to that and divide by 4. That integral is equal to this evaluated from 0 to 1. Okay? So remember what we do next in this process. We plug in 1, get a value, and then we say minus, and we plug in the 0. All right? Fortunately for us, we don't have to worry about the 0, because for this function, when I plug in 0, I just get 0. So that's 1/3 minus 1/4 minus 0 minus 0, right? Which I don't really need, but just to show you that that's typically what you do with that lower bound, all right? So my answer then is just going to be whatever 1/3 minus 1/4 is. That, of course, would be what? 4/12 minus 3/12. 1/12. Okay, and that's that little area. We thought it'd be pretty small. My picture is probably a little off scale. It should be 1/12 or 1/12 of that box region right there. Okay, I hope that helps.